I was actually thinking I forgot what the topic is, but it's nice to see generic types because I was actually thinking of that when I saw the PR um, that Bolivar put in with the being able to sum doubles and integers, because it seems like that might be a good use case. But anyways, Malcolm, whenever you're ready.
Yeah. Yeah, I haven't seen that. I haven't been looking closely at that the side projects, but that sure sounds like something that it would be good for generics for. Um, so as I said earlier, I do have my daughter next to me today. That's one of the reasons I've had trouble making it, is childcare. So she'll be joining us a little bit.
No worries.
And uh, we've got some Play-Doh over here, so we'll see how long her lifetime of attention is for that. So I picked this just like the
You
memory one.
can't
I picked this.
remember you can't
Uh,
control lifetimes. You can only annotate them. It doesn't actually
that's
change
that's
anything.
that very much matches my parental philosophy. um, yes. So I picked this chapter on purpose, just like with the memory one, because this is a topic that I didn't understand very well. I think I made more progress on the memory one than I made with these ones because there's a lot going on in this chapter. Um, and I kind of feel like they should have been at least two separate chapters, and maybe they should have been two separate weeks for us, but here we are. um, but I think I made a little bit of progress on my mental model for these things. So that was something at least.
Yep,
So for the
Malcolm.
learning, yeah, go ahead.
Sorry, if don't feel rushed. So like, it's better if we maybe add an additional week
Oh
if we
yeah.
need
Well,
to.
you know what I did was I just kind of backed off some, it's really chock full of technical details, and
Hmm.
I backed off that a little bit, and I just focused on like what are these actually used, like what situations are these actually useful for?
That's perfect.
Yeah. So we'll do that. And so I said that maybe this should hi maybe this should be um two different chapters, not just for us, but for the book. But the closest that they came about explaining why this was yeah. Hey, Mooney, could you just go play with Play-Doh? Um, sorry, one second. All right, sorry about that. So the closest that I've got to understanding why they put all these things together in the same chapter was this little bit at the end of the chapter, which was generic type pattern parameters let you apply the code to different types. Traits and trait bounds ensure that even though the types are generic, they'll have the behavior that the code needs. So those two things I think fit closely together. And then you learned how to use lifetime annotations to ensure that this flexible code won't have any dangling references. So whoa, all right, hold on, hold on. Sorry, she slipped out of her chair. And he fell in your cup, I know. So the dangling references part is the part that was like, okay, I don't totally see how this fits in, but the closest connection that I got was that it helps you annotate your code in a way that makes the behavior predictable. So I think that might have been their thinking with connecting all these ideas. I still think lifetimes probably should have been its own thing. I think it was different enough. So anyway, let's start with generics. So let's say that I had two functions that swap seeds. One of those seeds was yummy seeds, so the types of seeds that we can eat, and the other one was random seeds, as in the seeds we set for random number generators. So these are two different things, even though they're both seeds. One has I happen to use string literals here for the first one, and for the second one we've got I32. So these are swapping tuples, The location of the first one gets swapped with the location of the second one. So generic functions, these are tools to solve this problem where we have identical behavior, but because of the fact that we're dealing with a typed language, as opposed to something like R, we can't just say, okay, you know, anything that's subsettable can be swapped. Yes, you did make a whole mess. Congratulations. So in this particular example, I wrote two separate functions to do this swapping. And I'll just go and run. I have the playground open for all of these. So you know this. We've got sunflower seeds and pumpkin seeds, and then 42 and 1, 2, 3, 4, my two most common seeds when I'm setting seeds. And so I swapped their order. So before and after, we have sunflower, then pumpkin, and then pumpkin and sunflower, and then the same for the seeds that get swapped. But with generics, we don't have to force ourselves to write a specific function for this problem. And so this is, if you've got experience with other type languages, you've probably encountered this type of idea before. But I like the way that Rust does it. It feels a little intuitive to me, more than some of the other ones. So what we can do is use a type annotation. So by tradition, this could be anything, but by tradition, it's a capital T for the first one, and then U, and then B, and so on. And so I'm saying that this function, what it's going to do is it's going to take a tuple of a given type, and so both items in the tuple are going to be the same type, and this is my first time doing a presentation with my kiddo, so this is a fun adventure. So we're restricting this function in one sense, and we're opening it in another sense. So the opening part is this T. We're saying that this T can be anything, and the other sense we're restricting it because I'm saying that the two types of this tuple have to be the same, and the return type also has to be the same. The two items in the tuple need to be identical. So this is one thing that I think is kind of cool about these generics is that we are both generalizing it and we're also restricting its behavior. So now swap seeds will work.
A point that maybe you're going to make anyway, but I just note that I think that that's one of the only two functions you can define with that type signature, right? Either swap or just return the pair back, right? If you don't add any traits or any constraints, right?
It was actually hard to come up with an example that didn't use traits. Yeah, that's an interesting point. So this was challenging. That square, those are my friends that I'm talking to about this thing that we're learning. Yeah, we'll get to traits with it momentarily, but I tried to keep traits out of it. So they didn't keep traits out of it in the example in the book, and I wanted to do that. So this is one of the few examples that I could come up with that actually did that. Even printing things is hard because you need either debug or display to be a trait for the thing that's being printed or formatted. Okay, so this is my second one. This isn't super interesting, but that also runs. So I can also do more types. So here I'm saying that I've got two types that I'm declaring, T and U. And similarly, I'm making a restriction on the input. I'm saying that the first tuple has to have elements of the same type, and the second tuple have to have elements of the same type, but those two types can be different. So that's allowed. They can be the same or they can be different. That's me. Yeah, I know that person's not me. That's me right there. And so what I'm doing here is I'm swapping animals, as you'll see, swapping the habitats of animals. And so I'm basically swapping the elements of tuples. So I'm putting T and U and T together. So I've got a bird, robin, that lives in the forest, and a fruit bat that lives in a cave. And one is a string literal, and one is an owned string, an actual string, capital S string. So then I am going to swap them, even though they are these different types, and I could do whatever order I like on this because I've made it generalized. So now when I run this, the robin now lives in a cave, and the fruit bat now lives in the forest. And so this doesn't actually show the fact that it doesn't actually matter what T and U are here. This could be a string and this could be a string literal, or they could be numbers, doesn't matter. One thing that I almost didn't cover, but I decided to last minute, was that structs can also have generics in them. And so the simplest example that I could think of for something like this was an ID, where sometimes IDs are numbers and sometimes they're letters, and maybe we want to represent them in their just sort of the format that they come in. So we've got here a chimpanzee and a bonobo, and the chimpanzees are tracked with number IDs, but the bonobos are tracked with alphanumeric IDs. So animal works just fine with either of these. What are you asking about a marshmallow about? She's asking Siri something about a marshmallow. So chimpanzee 23 and bonobo A34 work fine here. Yes.
Quick question. So it doesn't actually lose. I mean, I guess I'm trying to think about this. So I make a chimpanzee. Russ is going to make an instance of that type with the int type, right? So then later when I call it out, it knows it's an int, so it's fine. Okay. It just bothered me for a little bit because there's no traits on the int. So how does it know that it's printable? But it's okay.
Oh yeah, well they're primitive types, so they don't they just have them.
Well, no, I mean it's just type T in the thing. So if we had an implementation thing, we couldn't do
Oh
anything.
yeah.
But since we're using pulling the parts out, I guess we can. All right, I just had to think about that. Sorry.
Yeah, that could be.
Yeah.
That could be. I don't know if we tried to use a method, implement a method,
Yeah.
we might have to put a trait on it. I think when I was experimenting with this, I actually did do that, and then I decided let's make it simple.
Yeah. Interesting.
I think that's exactly what happened. Was I needed the debugger or display trait. So yeah, so I tried to simplify these examples to be just kind of show exactly what I needed to show as best I can. No, I don't want you to open my phone. So speaking of traits, sorry, 1 second. All right, so traits. Let's say we had a struct who is a bird, and we've got name and wingspan. Speaking of display, I decided that I don't think this gets covered in the chapter, but one of the first times that I ever encountered implementing my own trait was I wanted to be able to display something without debugging. I wanted it to be displayed nicely. And I think writing print methods in R is what gave me the appetite for doing this. Like I wanted an object to be printed in a nice way. And so I looked it up, and it turned out that what you needed to do was you needed to implement the display trait for the object that you were interested in displaying, and you needed to write this format function. That's what is declared. So there's some technical details here. This definitely confused me when I first encountered it. So I won't go over these, but this is a way that we can display bird without using the debug statement. We can use just the plain one display. And what's fun about this is that you can display it however you like, just like in a print method in R. And so for these, they display the bird and their wingspan. So in the middle we have the name of it, and then we have the wingspan on either side. So that's what's happening here in this little bit. So this was fun. But I thought that this was an interesting example because in the book we go right to making our own traits, which is useful. But Rust has, I know, but Rust has a lot of traits that some of which are easy to automatically derive, and some of which are not, like display. And so I think learning to work with Rust's traits is really useful. Yes, Starling. Yes. Can I help you? Okay. Um, so going to a little bit more of like what the book was talking about with us. One sec. I had to flatten out some Play-Doh. So I wrote two traits here. One is fly, and one is lay eggs. And when we're writing traits, we give it the definition of the methods that we want that trait to have. So this is a guarantee that we're giving a type of object. If a type of object has the trait fly, it needs to implement the method fly with this definition. And so fly is taking the self and returning a string. And similarly, lay eggs, you need to have a method that is lay eggs that takes the self and returns a string. So I wrote two structs to go along with this. The first one was bird. So birds both fly and lay eggs. At least most birds do both of these things. I'm just realizing now that it would have been fun to do some birds that didn't do some of these things. So for fly, I'm implementing a function, or a method rather, that is for bird. So I'm implementing the trait fly for bird, and then within that, I have the method fly. And this matches the method. And then similarly for lay eggs, I'm saying that the struct bird is also going to get the trait lay eggs. And so I take that function definition that we had before, and I write a method that matches that. So I've also got a bat. Bats fly, but they don't lay eggs. They're mammals. So I implement the fly trait for it, which is a little bit different than the bird's fly trait, or at least the fly, the version of fly that this has is a little bit different than the bird's. And then it doesn't get a lay eggs trait because bats don't lay eggs. And then finally, actually not finally, I have two examples of this. So I've also got an example of a function that is using generics, where I have a trait bound that is telling the function what it can use. So this is what we were talking about earlier, where it's actually pretty hard to write a generic that doesn't also come with a trait bound, because when we're writing generics, usually we're doing something inside of the function. And we want to be able to guarantee that whatever the thing is that has type T can do the thing that we actually need it to do. Would you drop? Oh, you're lying. And so what I'm saying here is that for the function fly home, this can take any animal of type T, but it needs to have the trait fly. So fly home and lay eggs is a different function than fly home. And it requires both the fly trait and the lay eggs trait. So now we've added an additional restriction to this function, which is that we need the animal to be able to fly, and we need the animal to be able to lay eggs. So it can take any animal that can do that. And in our case, the only animal that can do that is a bird, a bat. can't do both. So we've got a bird, we've got a bat. They can both fly home, but only a bird can fly home and lay eggs. So I'll open this up. Oops, wrong one. And run it. So the robin can fly, the fruit bat can fly, the eagle can fly, and it goes home and lays its eggs in its cozy nest. But if we also try and apply this to the last one, to a bat, it won't work. And the compiler tells us the trait lay eggs is not implemented for bat. So this is something that we're requiring in this function. So this kind of all together is something that won me over. This read around on this chapter was the way that we can generalize code while also enforcing expectations about the inputs and outputs of that code. So it's to me, it's a little bit, I had never really encountered anything like traits before. So it's still a little bit hard for me to wrap my mind around, because it's not quite the same as inheritance and other ideas from object-oriented programming. So it's taken me a little bit, but it's really starting to win me over. This
It's a little
type
similar
of design
to Java's interfaces, right? I don't know if you use Java at all.
Yeah.
Interfaces. They're
Yeah.
similar.
Yeah, which is maybe why I never got Java either. Yeah, but this definitely is like this idea, this way of interacting with code and enforcing these expectations about the code is something that's begun to win me over. And so that sort of that statement about it is where I think the connection with lifetimes is you're writing down expectations, your code in a particular way. So generics and traits are expectations about inputs and about behaviors. Lifetimes are expectations about references and how long they should be able to last. And I have to go pick up a zebra. Maybe you can see where my animal examples came from that I wrote for this. She's not eating any seeds right now. She's eating peanut butter panda puffs, but that was too much to type. So okay, so lifetimes. So traits are very tricky to me. Lifetimes are also very tricky to me. But there are a few things in studying this chapter that finally kind of clicked for me. I don't think my mental model is like there yet with lifetimes, but I think I made a little bit of progress. And one of the things that I made a little bit of progress on was this quote from the rust01, which I haven't read. This is about unsafe Rust code, but I encountered it on a YouTube video about lifetimes, which is that lifetimes are named regions of code that a reference must be valid for. So I thought that was an interesting way to think about it, that it's this space in your code for which a reference has to be valid. And so as we brought up earlier, these are expectations about lifetimes. We can't actually change the lifetimes by explicitly annotating with it. So this is another way when they sometimes call these generic lifetimes. And I think that is because of the fact that we're not actually able to, if we have two different objects, we can't actually change their lifetimes through a function signature or whatever. But we can declare our expectations about it. So, yes, I'm glad you got out and didn't fall out this time. So this time I've got two structs, predator and prey, and they both take ecosystem. Now I have a function describe hunt, and I want it to be able to take a reference to both of these objects and to return a string literal here. And so if these two objects have the same type of ecosystem, then the predator can hunt the prey. But if they're in different ecosystems, then no hunt occurs. And so this is what we're returning. So this is always a reference, but it's okay that it's created and put out by this function because these things live in the binary. That being said, if you try and run this without lifetime annotations, Rust will complain. I do know something different about your hand. It's all blue all of a sudden. This is your chance to get all blue while I'm not looking. So
Does
let
that
me
apply
go.
to everybody?
Yeah, I'm not looking at any of you. I'm looking at the screen. So if you wanna color yourselves blue, go ahead. Oh, she's gonna color me blue. This is really her shot. Her shot. Okay, so I've got a lion, and a gazelle, and a deer. All right, so the lion and the gazelle both live in the savannah. The deer lives in the forest. The lion can hunt the gazelle, but it can't hunt the deer. So let me just go and run this, but I'll show it before, after having already written these. I know they look exactly the same. But if I remove the lifetime annotations for this, even though this is really not a very complicated function, Rust is going to complain to me. It says that, we're expecting a lifetime parameter for this. And so the two conclusions that I ended up
one of
reaching
these
about
cases where
this,
you could put a static on that output?
maybe,
Because it does live forever.
yeah,
Oh,
that
yeah,
works.
okay.
Yeah. So static, I don't have a slide about static, but static is a way of saying that, the expectation that you're writing is that it will live for the entire space of the program. So the region of code that it should live for is the whole code, which is totally fine for string literals because they're written into the binary, and so they are accessible throughout. So that's totally fine. I didn't think about doing that here, but the compiler suggests that I annotate it more broadly with tick A. Those are yours. And the reason is that we're taking in references and we're spitting out references. And Rust apparently, even if your implementation in your code is like obviously safe, when you're talking about a function, Rust is considering different edge cases that may not be in your code. And so it expects you to define those lifetimes because it's worried that one of these references is not going to be alive long enough for you to do what needs to be done without becoming a dangling reference. And so this was something that was a little bit hard to reason about because Rust is really good at saying like, well, I looked at your code and it's fine. Like what's happening in this code is fine. You don't have anything weird. But in this particular case, it seems to it considers situations beyond your code where it could go wrong. Like if somebody else used your function. Yes, you can sit on my lap. The reason is that by default, Rust will define predator and prey as having two separate lifetimes. And then it looks at this reference here and it says, well, I don't know which of the two lifetimes this should actually get. So one solution is use a static lifetime. That was cool. I didn't think about it at the time. But the other one was to just, when I say this way, here, I'll just copy and paste this because this is exactly what I have. When I say it this way, I'm saying that, I don't actually need that level of flexibility where predator and prey have different lifetimes. It's because I know exactly how I'm using it in my code here, and I can say, well, it's fine. They just all have the same lifetime. So they just need to be valid in the way that they are in my code. And that's that. And so this is greatly restricting what this function could do, but it is working just fine for our example. So finally, you can also use lifetimes in structs. And so here, I've enhanced ecosystem to be a struct. And so now it has a variety of details about the ecosystem. And in the animal struct, I'm now taking a reference to an ecosystem. So rather than using a duplicate of Savannah like I did before, I can now have a reference to the same ecosystem without having a duplicate. However, that requires me to have a lifetime declaration. And so this is another simple one. because I only have one reference in here, and lifetimes are all about references, managing references. And so I just make animal have the same lifetime as ecosystem. So now Rust is going to verify for me that that is true. One tricky part about this, although it's not that tricky because the compiler will tell you exactly what to do, is that you also need to have these lifetime declarations for any implementations that you have for your struct. So I'm going to be able to describe the animal with this function, but because animal has this lifetime annotation, it's beautiful. Then we need to be able to do that in the implementation for the function to describe as well. So I declare an ecosystem, and this time these two different animals, the predator and the prey, so one's a jaguar, one's a capybara, they're both getting references to the same ecosystem. So that's convenient because I don't need to make a new one, but it required me to declare something about the lifetime of that object. So let me run this and make sure that it still runs. So this tells us a little bit about the animal and where it lives. So those are the many details that we got in those chapters. I feel like those were the big things. And then we've also got like a ton of little things throughout the chapter that were like, technical edge cases. And I know I don't have a forest. I'm talking about animals that live in the forest. All right. And that is the end of my slides. So if you have any questions for my daughter, she's got all the answers.
Thank you. Could we go back a few slides quickly?
To which one?
To one more. Just maybe this one, or maybe the one previous to it. Just because I'm having a super hard time interpreting or understanding what is actually going on. Maybe others are as well, maybe not. So essentially what you're saying is within the context of this function itself, in its limited scope, the lifetime is not super important, but the lifetime is more of a contract when you're potentially writing unsafe code that's then going to implement that function, and potentially one of the references is dropped over the expected lifetime of the function itself. That's
right.
the idea.
Yeah. Well, not the function itself, but how it's whenever it's being used. Right. So if I were, throughout the I chose not to use scopes in this. They use scopes as an example because it's a way of basically forcing a lifetime. But scopes themselves aren't lifetimes. It's just that a thing's life ends at the end of its scope. And so if I were to define, an outer scope that has predator in it, an inner scope that has prey, and then later tried to use that at the bottom of the outer scope, then this wouldn't work. But first it would complain that it doesn't know what the lifetimes is. And then if we define this, nothing's changed about the lifetimes. We've just made it explicit. We expect them all to have the same lifetime, or more specifically, that the minimum, whichever the smallest lifetime is here, is enough for those references all to be living still. Yeah, lifetimes are tough though. I think I only like inched forward a little bit. Oh, Looney.
I agree. They are a little tough because they aren't the same as scope for one thing, right? Like you said, it's very confusing because some places actually do try to make them sound like they're the same. And again, it's, just wrap your head around the idea. All you're saying is that I'm claiming this is the case. You check and make sure I'm right. And the purpose is, I guess, that the compiler can't figure out. How could it, right, from the function definition, what the lifetime of the return type is supposed to be? In the book, they have an example where you're returning like one of the two things you brought in.